back to being. So this is my second talk, and so I want to get into second and higher order freeness, and it hinges on something which we call partitioned permutations. So it's a combination of partitions and permutations at the same time. Let me just review a little bit of what I said last time. So we're going to have a non-commutative probability space, and the idea is that freeness gave us a universal rule for computing mixed moments from individual moments. So what that means, if you have two random variables, x and y, and you know all the moments of x and you know all the moments of y, there's a rule for computing the moments of monomials in x's and y's, so x squared, y cubed, and so on. And so there's this basic rule about vanishing of mixed cumulants that I talked a little bit about last time, and Heilun mentioned it some more, and it just repeats what he said, that the nth cumulant of the sum is the sum of the nth cumulants because all the other mixed terms go away. And that was the driving force for the R transform, because that meant if you knew the R transform of x and you knew the R transform of y, and you knew that x and y were freely independent, then you could find the R transform of the sum. And then you could go back and find the Cauchy transform of the sum. And from the Cauchy transform, you can find the spectral distribution of the sum, which was the big breakthrough that Wojciechowski found. This was a way of finding the spectral distribution of the sum of two free random variables. There's also a rule for products, but there's another variation of it, which is given by this formula. So if you have two free subalgebras.
Sorry, could you hear me?
Question?
Yes, I have a question.
Oh.
I think that there is a typo. If you look on the number of variables in this Kn, in this formula involving summation, yes?
N minus 1. On the left-hand side.
On the left-hand side.
Oh, that should be a 2. That should be a 2, I'm sorry, yeah. A1, every entry is the same, A1 plus A2. Yeah, so A1 and A2 are free. And this is the one where we use multilinearity. So you look at all possible ways of putting a 1 or a 2 in. I1 up to IN could be either 1 or 2, but they're all 0 except the case where you either have all 1s or the case where you have all 2s. Okay, sorry about that, thanks. So this is a kind of a convolution product. So you have two strings, from one subalgebra, another one from another, and they are free, and then you alternate. And it says this is the moments of one and the cumulants of the other summed over partitions, but you have to change. You put a pi here, and there's another one called the Crevera's complement, which we'll explain in a bit. And this formula has analogs in convolving, taking traces of products where you took, you had two matrices and you conjugated one by a higher unitary, and then you integrated out the higher unitary. So sometimes it's called the Itzikson-Zubair-Harris-Chandra formula, but that was for a finite n. And there was an expression involving 1 over n, and when you let n go to infinity, you got something like this. So that was and in the free limit, of course, things get simpler. You don't have all these higher order genus terms. You just have the genus 0. Okay, so I'm going to talk now about these higher order non-commutative probability spaces. So first, I'm just going to talk about a second order. So here we start with an algebra again over the complex numbers with the unit. Now I'm going to insist that this linear functional phi right here is tracial. Before, I didn't require that, but now I'm going to assume it's tracial. And now I'm going to also assume the existence of a two-variable linear functional. So it's multilinear, so there's two bilinear, and in each argument it's tracial. So each argument is going to be an element from the algebra, and I insist that if you cyclically permute the element, if it's a product and you cyclically permute them, it won't change the answer. And then the other thing is, I'm going to insist that if you put the unit, shoot, that should have been a comma 1. Sorry, it's 1a and a comma 1. If you put a 1 in either slot, you get 0. Okay, so why would you ever do this? Okay, well, so if you take an element and you take these numbers, we call those the moments. And if you put a to the k and a to the l, you call that the mkl fluctuation moment. And they came from studying these endpoint functions for random matrix ensembles that I think goes back as far as 3 papers that Dyson wrote in 1963.
Sorry, you've got a quick example of this second
Yes, there is.
and by matrices.
Yeah, right here on the bottom of the screen. I'll get to Just let me get there and we'll answer your question. So let's start with some random matrix ensemble. For example, it could be a Wishart matrix, the GUE matrix, GOE matrix. A large collection of examples will have this feature. So we take the Lth power, take the normalized trace, take the expectation, then take the limit. We suppose that limit exists, and we call the number m sub L. Now we take the covariance of traces of powers. Okay, notice that here there's a scaling thing we have to do. You don't normalize the trace now. Otherwise, it would go to 0. So you don't normalize the trace. And you take the covariance, you let n go to infinity, and you get this 2-index moment. Then you can take this third cumulant of a trace of powers. Again, to make the scaling come out right, you have to amplify it by multiplying by n. Otherwise, it goes to 0, and you get a third order moment. M sub L1, comma L2, comma L3. And so if you have such a matrix, then you could, to make a model up here, you would take the algebra just to be polynomials in a single variable t. And I would say, what do I do to a polynomial? I apply the polynomial to the matrix, and I run it through this thing. I get some number that depends on the polynomial. If I have 2 polynomials, P1 and P2, I do the same thing, and I get a bilinear thing. And what about the tracial part? Well, okay, everything's commutative here, so it's that maybe that's a bit vacuous. But if you put a 1 in here, remember I said that cumulants vanish if you put a 1 in any slot. So that's why you have that other axiom. These are classical cumulants.
Classical.
Yeah, so on my convention is An equals nth classical cumulant and kappa n equals nth free cumulant. Yeah, I hope I was consistent all the way through with that notation. Just because you need both cumulants in play at the same time. Okay, so the problem that led to higher order freeness was this, that we saw in first order freeness, you could compute mixed moments from individual moments if the operators were free. And then the question was, can you do something for fluctuation moments or third order moments?
Why do you take the vector value?
Why would I say that, for example, here? Well, I mean, I guess the way we interpret this problem, lots of people studied linear statistics, what are called the linear statistics of some random matrix model in statistics, and they wanted to compute this. So we said, okay, in order to get some traction, let's take a problem that people have already decided is interesting and see what we can, how can we contribute to it, rather than just sort of make something up. So it was really because in classical statistics, this is what of course, this is the same as kappa 2, and this is the same as kappa 3. So at this level, you don't see it. It's when you went to the next level, kappa 4 and K4 are not the same. So, yeah. Oh, why to take the covariance? Okay, well, okay, maybe I'll tell you why people are were interested in this. You see, with this scaling, if I didn't put this in here, it would go to 0. And then same with the fourth cumulant, the fifth cumulant. And that would mean that this random variable has the property that all its cumulants go to 0, except possibly the first and the second. Now, what's the one random variable that has that property? Wrong. It's the classical semicircle, namely a Gaussian. Gaussian, yeah. So in the problem that people are doing is that this is sometimes called a central limit theorem, because these random variables converge. You get, for every exponent, you get a different Gaussian, and you get a Gaussian family. Not only is they individually Gaussian, but they're collectively Gaussian in the sense that all mixed cumulants of order 3 or higher are 0. Right? So, you know, if you want to make a Gaussian vector, each entry is Gaussian, but there's a relation between them. They don't have to be independent. But what they do happen to have to satisfy is that the third, fourth, fifth cumulant is always 0. Right? So that's what you get. You get a Gaussian family, and now we're just computing the covariance between them. And that once you know the covariance between the things, you know the entire distribution.
There is no relation by 5.
Because there isn't. No, so in this theory, you can just, and you could in principle just arbitrarily decreasing. Whether it would be interesting is another question. So all the examples that I know of all come from random matrices. Or
example where algebra is empty?
yeah.
The product of traces.
Yeah.
You want trace of, you want the normalization. Oh,
Yeah. I don't know of one right now. Yeah. So to me, the interest is all from these random matrix ensembles, or things that you got from random matrix ensembles in some case.
Would that be related to Wigulescu's asymptotic?
Yes. Oh, yeah. Definitely. Yeah. No, that's all. This all came from those examples, because for certain examples, these things can be explicitly computed. Okay. But the crucial thing was to think of these cumulants as moments. Notice that we switched sides here. So what was a cumulant, I'm now interpreting as a moment. And now to make this theory simple, I'm going to take cumulants of the cumulants. Right? Yeah, so we'll explain that. Yeah, it's coming. Yeah. Okay. Any other questions? Yeah. The scaling, you mean? Yeah. So, no, I mean the scaling is within the trace. Yeah. Yeah. So this is the expectation of the product of the unnormalized trace minus the product of the expectations of the unnormalized traces. Yeah. So for the G UE, these things are completely worked out, and this essentially I'm not really certain. It's just sort of a folk theorem almost. I mean, I think I even learned about it from something in the physics literature, but it took me a while to realize what they were saying. But in the end, it is this. And Daniel is going to talk about what these things mean when you don't assume, when you just take a Wigner matrix, where you don't assume anything about the distribution of the entry, you don't assume it's Gaussian, and some very interesting things will happen. We'll hear about that on Friday. Okay. Go on. So the idea of higher order freeness was, you know, the fluctuation moments of one ensemble and the fluctuation moments of the other ensemble, and you want to find the fluctuation moments of sums and products. Is there a universal rule that does that? Now, I'm not really going to tell you what the universal rule is, because I thought I would focus on this things between cumulants and moments and these equations, which is more closer related to topological recursion. So I'm not going to tell you what that is, but there is a rule, and that's how it got started. Yeah, I should say a little bit of the history of this. That, yeah, Andrew's not here, but my participation in this subject started with a paper I wrote with Andrew about 20 years ago, where we looked at Wishart matrices. And we computed the fluctuation moments. And we noticed that if you had independent Wishart matrices, there was a rule for computing the mixed moments in terms of things one and the other. And then Roland and I got together and we turned it into a rule. And at that point, we just had a rule, like the rule that we had for Voiculescu's rule. It said, if you had alternating product of centered elements, then that was centered. And that gave a rule for computing things. And that's, as remember, Palin did that example right here yesterday. So we had a rule like that for moments. And then a couple of papers later, we came up with the idea of what a cumulant was. So that at one point, we had no idea what the right cumulant was. And now that's what I'm going to tell you about, is what cumulants are. Okay, a crucial thing was, one other thing is that, yes, we assumed that that the matrices, what we were trying to build something that matched what happened with the matrices rather than just build the theory from abstract. We said, whatever we do has to work with a whole bunch of standard ensembles. Otherwise, we're not doing the right thing. And then the other thing is to switch to writing instead of working with partitions, non-crossing partitions, we switched to permutations. So a small change in perspective made things come out easier. So let me just say something about that. So any permutation can be written as a disjoint union of cycles, and this produces a partition. These cycles produce a partition, sorry. These cycles give you a partition. But of course, it's more information because inside a block, you remember the order of the elements. In a normal partition, you don't. Okay. So we let this sharp sign be the number of cycles in the cycle decomposition, and of course, including cycles of length 1. You let this is what we call the length is n minus the number of cycles, and that's the number of transpositions you need, the minimal number of transpositions you need to write the permutation as a product of transpositions. You have a triangle inequality because if you have a product here, then you can, that's obviously that you can always take a product for here and a product from here, and that'll give you one for there, but maybe you can do better. So you get the triangle inequality. This permutation with one long cycle will always play a special role. And often I'll just call it gamma. Well, it has one cycle and its length is n minus 1. And yes, this is an observation of Philippe Bion, although I think there was earlier cases of this in literature, but I think most people in free probability learned about it from Philippe's paper about 25 years ago, is that if you take a permutation, and yeah, the product of these two things is gamma n, And we always have that this is less than or equal to that by the triangle inequality. But if we have equality, that will happen only if the permutation is non-crossing. In addition,
What is gamma?
gamma is this guy right here, this permutation with one long cycle.
Gamma n.
Yeah, so
It was also that.
it should be an N, yeah, I'm sorry. I'm having trouble with my subscripts, sorry about that. And this other thing is what's called, is the Crevasse complement. So you take pi inverse of gamma, and that plays the Crevasse comp role, and that's this guy right here. So that's not the standard way of defining it, but I think in the next slide there'll be a picture. Yes, okay. So here I'm drawing my partitions on a circle now. So pi has got 1 as a singleton, 2 as a singleton, then 3, 4, 7 is a block, 5 and 6 is a block, and then we have 8, 9, 10, 11 is a block, and 12 is a singleton. So pi has 6 cycles. There's 12 things, so the length of pi is 12 minus 6. You can compute this Crevasse complement. It's just pi inverse gamma. There it is. You just do the multiplication. It's got 7 cycles. So the length is 12 minus 7. You add this, you get, yeah, let me see. It's, that's not right. That should be 6, right? Because it's supposed to give you, it should be 6 and 5. 1, 2, 3, 4, 5, 6. Yeah, that 7 should be a 6. Sorry about that. Yeah, okay. So it adds up to 11, which is 12 minus 1, which is the length of the one long cycle. But you can see the little bit of topology here. So how do you see this Crevasse combo? Well, you take your circle, you put 1, 2, 3, 4, 5, 6, 7, 9, 12 around, and then between 1 and 2, I put a 1. Between 2 and 3, I put a 2. And so in each of these gaps, I put a little green number. And now I just start here, say at 1, and I move around this space, and I get 1, 2, 7, 11, 12. Look, 1, 2, 7, 11, 12. So it exactly captures the this thing, and you can see that this has to be non-crossing because I'm just filling in the gaps between something that's non-crossing. In addition, this is the biggest block I could put in here that wouldn't create a crossing. I mean, if I tried to connect something across this gap, then I'd create a crossing. So that's the usual definition of the Crevasse complement is you take 1 to 12, and then you put in interleave these other numbers, and then you find the biggest partition of the green numbers that doesn't cross, that you can stick in there that won't cross on the whole thing. Okay. Now, one thing we'll have to do is write something like this, which it's going to look a little strange because I'm thinking of pi as a permutation and as gamma, and what is the soup? Okay, so I hope this notation won't be too annoying, but I like this idea of coercion. In computing, sometimes you can coerce something down to a lower status. In other words, a permutation has more information than a partition, but this operation kills that information, that higher order information, and just treats it as a partition. Okay, so hope that's not too crazy. Anyway, that's my personal taste. Okay. So the way that we came up with these cumulants, so this is in a paper with Benoit Collins, Piotr Snidey, and Roland Speicher from 15 years ago, is we combined permutations and partitions. So we're going to start with a partition and a permutation, so that every cycle of the permutation is contained in some block of the partition. When that happens, I just write pi less than or equal to u. I let PSN be all such pairs. You can define a binary operation where you soup the partitions and take the product of the permutations. You have to check that this thing on the right-hand side still satisfies that condition, but you can do that. You can put a length function on these objects. So you take twice the length of the partition and you subtract the length of the permutation. Okay, that looks a little weird, but it has some very nice properties. And I think down here, which I'll get to, is maybe the best one. So, and then you have the triangle inequality. Okay, that takes a little work to prove that there is such a triangle inequality, because there's this minus sign here. And on my last lecture, I'll try and turn some of these things into something involving some graphs. And something will, well, when something is nice, the graph will be a tree. So I think there's a way to interpret all of these inequalities and turn something into a tree, which makes it easy to understand. So in general, we want to deal with, on the previous thing I just did, the first order moments, second order moments, and third order moments, but I actually want to do all moments of all orders. So we need this little notation here. So if I have, I'm going to think of this as R cycles. And each cycle has either M1 elements in it, M2 in the second one, and so on up to MR in the last one. So I'm going to make a big permutation with these R cycles. And yeah, so this is why I was sort of leaving out those ends, because I don't want to write this in a formula because it's too big. So each time I'm going to let gamma be this long thing. And if pi is in SM, then you have this inequality with equality if and only if pi is planar with respect to gamma. So let me try and explain what that is. I'll just notice that if gamma has only one cycle, then this is already just one block. So it's, when you soup anything with something with one block, you just get one block, which is gamma again. So yeah, if this is gamma, then what's the calculation? Look, I get 2 times the length of gamma minus 1 times the length of gamma. So I just get the length of gamma, which is the previous formula for that in Philippe had for characterizing planar things. So I think, yes, here's an example. So this would be the case R equals 4. Gamma is 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Here's a pi. And so the picture, and there's many ways to draw these pictures, but here's the one way I drew it, is that you're going to put the numbers, okay, around the circles in clockwise order. And then the challenge is, can I draw the cycles of pi on these circles in such a way that the cycles do not cross? So you're given a permutation, and this is a case, and here's a way. So I mean, you see how this thing goes around the back here and there, over there, like that. So you got to do a little trial and error to find, if there is a way to find it. I mean, you can check this equality, you can compute this, you can compute this, and you compute this, and that will tell you whether or not it's possible. There is I think you could even write an algorithm, which I won't tell you about, but I think it's a completely machine reducible thing, because you can, when you have 2 circles like this, you shrink one of these edges to a point, and you join the circles together, and then you just keep reducing it until you get down to 1 circle. And you know how to do it on 1 circle because you can do it with triangles. And then you do kind of a homotopy argument where you stretch it apart. And so I've seen somebody do this, some graph programming with graphs, that you try and make a graph that satisfies some constraints. And I even think in Mathematica, if you give it a list of edges and vertices, it's got an algorithm where it draws the graph and it keeps flashing on the screen until it reaches some kind of minimal energy configuration, but it usually comes up with a nice picture. So I think you could almost do that with this problem here. Anyway, that's the separate subject. Okay, and here I just went through the calculation, showed that this is a planar object. So those are the genus 0 things, the ones where you can draw it so that you can draw it on a sphere. You don't need any handles to make it non-crossing. Okay, so I'm going to come back and talk about second order things now. So I just repeated this inequality from before, but now let's just do the case where you only have two things. So I'm going to suppose that pi sup gamma is only one block. That means that's equivalent to saying that there's a through cycle, right? Because gamma has two blocks, one here and one there. And I claim after suping, there's only one block. That must mean a block of pi connects the two blocks of gamma. Or in the picture, it just means there's at least one block that goes from one circle to the other. I didn't put arrows on here, but you go around each thing in clockwise orientation in this picture. Okay. And I'm going to let S, N, C, M, N be the non-crossing permutations on an MN annulus. So this is the first case where you really have to make a distinction between partitions and permutations, because it's not just the blocks, it's the order in the blocks. If you wanted to make it model some random matrix calculations, it's the order that you go around that makes a difference. Okay. So let's talk about some cumulants. Okay, this has got a lot on this. So let's take a non-crossing partition on one circle with m elements, a non-crossing partition on another circle with n elements. And okay, I meant to say NCM cross NCN. Sorry about that. That's some late night typing, and yeah, that's what I meant to say. Okay, so that would be the case when there is no through cycle. On each circle, you have a non-crossing partition, but there's no block of the partition or cycle of the permutation that connects the two circles. And that's the thing we were trying to find. And let gamma be gamma m comma n. And I'm going to choose a cycle on the one partition or one permutation, and then a cycle on the other one. And I'm going to make a partition U where I join these two things to make a single block. And every other block is a cycle of pi 1 or a cycle of pi 2. Okay. I have various ways of drawing this, but I don't really like any of them. Or there's one that I really like, but nobody else likes. So I'm not going to show you anything of how to draw this. Maybe Octavio will have something another way. Okay, so let's just do a little calculation. The length of U is going to be, okay, well, you have to do this calculation. It's the length of pi 1 plus the length of pi 2 plus 1. So the length of this partitioned permutation is the length of pi plus 2. And what about, yeah, we need this. The sup of U with pi inverse gamma. Okay, U is already bigger than pi, so there's no harm in suping U with pi. That's still U. And then by the associative law, I sup pi with pi inverse gamma, but that just gives you gamma because each pi already lives only on one cycle, so nothing is gained there. And so, but U connects the two blocks of pi, of gamma, therefore you just get one block. So the purpose of this line was to show that U sup pi inverse gamma is equal to 1. And so that means when I multiply these two things according to my rule, I get 1 m sub n comma gamma. Right, so remember the rule is you multiply the permutations So that just gives you a gamma, and you soup the partitions. So this, oh yes, I haven't defined. So here I break my own rule. And if I write 0 pi, that means explicitly interpret that permutation as a partition. Okay, otherwise it would just be too confusing. Okay, and so this has the right thing, and let's just check. Yeah, so here, how do you compute the length of this guy? Well, it's twice the length of this minus the length of that, so it's just the length of that. And therefore, we add this up. I've already computed the other one. So I just get length of pi plus the length of pi inverse gamma plus 2, which is the length of gamma plus 2, which is the length of this thing here. So it's an exact factorization. We have the product is the thing, and the length is exact. So this is like on a geodesic. You go from one to the other and then on to the third, and there's no wastage. And those are and that's been a standard thing in this business, is that tells you the geodesics give you the non-crossing stuff. Okay. No, it's not unique. It's just one possible path. And so the objects that we're going to look at are all things that lie on a geodesic up to this guy here. And now I'm going to tell you what a second order cumulant is. So a second order free cumulant. Yeah, there's no second order classical cumulants. So it's safe to say we can drop the free word now. So I'm going to say it's kappa u pi. And now I'm just going to do what I did before. For each cycle of pi, I'm going to take the number of elements in that cycle, and I'll take the free cumulant that goes with that. But for those two things that glued together, I introduce a new number. I call it a two-variable one, where I say how many things layer on one circle and how many on the other circle. Those are all integers, yeah. That's right. The smallest it can be is 1. Yeah, right, because the cycle has to have at least one element. Yeah. So that's, yeah, well, I mean, it turned out that it gave all the right properties. That was how you justify the definition, that freeness was vanishing of mixed cumulants. And yes.
So for the definition of U,
Yeah.
What's going to happen if we perform the one part first from sequence prime?
Okay, then this condition that the length of this plus the length of that equals the length of this would not be satisfied. Okay, this would be too big. Remember, this number is always less than or equal to that sum.
Does it mean this is a higher genus?
Then it would be a higher genus contribution, exactly. Yeah, okay. That's right. So in this theory, we just stayed away from them. But yeah, I mean, I did do one thing where I connected the Weingarten function to the Möbius function of this thing, taking into account all orders. But that paper is still sitting in my desk drawer because I was waiting for somebody to be interested. And it just looked way too far out. Anyway, okay. So yeah, here's a picture. So in order I took a non-crossing partition on each circle, and then I colored that sort of peach color, the cycle that I chose. So on the outer one, I chose 3, 4. On the inner one, I chose 10. So you see that U will have, 3, 5. So U has this one block, 3, 5, 10. All other blocks are just cycles of pi. And here I just computed and showed that the geodesic equation is satisfied. Okay, it's an easy thing to do. And then the question is, what is the contribution of this picture? Well, I have these marked blocks, one of size 2 and one of size 1. So I get a kappa 2, 1. And then I have 4 blocks, each of size 2. So I get a kappa 2 to the 4th power. And then there's one other block, namely this little 4 at the bottom, which has 1 element. So I get a kappa 1. So the contribution of that particular partition permutation is kappa 2, 1, kappa 1 to the 4th times kappa 1. Okay, and now
Could you cross the 11i thing? You merge the.
okay, now you forced me. Okay. I'm going to have to show you my picture.
You asked for it.
Yeah, that you asked for it now. I was just waiting for someone to do that. Okay. Yeah, so yeah, this is the kind of picture that a topologist would like. Okay, so here's what I'm going to do. So what do I have? 1 to 7. So I'm going to draw in all the blocks except the orange ones. So I'm going to do 1 and 7. And then I'm going to do 8 and 12. Okay, so 8 and 12. And then I'm going to do 9 and 10. Now, yeah, there's a little bit of ambiguity when they don't go across, whether you draw it up or down. And so I'm going to do it this way. And then I have 2 and 6. And I haven't finished yet. And then I've got 4. Okay, now here's the weird thing. I'm going to make a cylinder. And so the idea, I'm going to take this cycle 3, 5. So I'm going to, yeah, let me see if I can draw this in an extra thick line. So that's going to be one end of the cylinder. And the other end of the cylinder is up here. And when you do this, you get another annulus. Look, I have a circle with 1 point on it, and the other circle's got 2 points on it. And this gives the order structure on these things. It says if you can stick one inside the other like this, then that's the geodesic equation in this set with a metric. Yeah. Yeah, so that's why we're here. To try and make a precise connection. So you yeah, so you make a cylinder by just doing it like this, and then you see you can ask what the order is. Because this other order is very complicated. And if I gave you 2 partitioned permutations and I said, what does it mean that one is less than or equal to the other? That might be hard to just discover from the metric conditions, but it's exactly that you can stick one inside the other. So maybe just not everybody's completely clear on that, but you can say for and on the level of partitions, you say that pi is less than or sigma if every cycle of pi is contained in some cycle of sigma. And if you take a cycle of sigma, you make a circle, and you put in the cycles of pi, they form a non-crossing partition of that circle, putting the elements in the order that they appear in the cycle of sigma. So in the case of gamma, there was only one cycle, and you just put the numbers in clockwise order, so that maybe you didn't notice that you were doing that. And then that would give the order on these things. Okay, so there's a second order cumulant. Yeah, so now I'm going to tell you what the second order moment cumulant formula is. So remember SNC was the non-crossing annular permutations that connect where you have at least one through cycle. And then, okay, I don't really have good notation, but I'm going to call PSNCMN primed to mean the non-crossing partition permutations where the pi doesn't connect the two circles, but U has one block, which is a cycle from one and a cycle from the other. And all other cycles are cycles of pi. And so we call that PSNC MN primed. And I take the union of those two things and I call it PSNC MN. And then the formula is, okay, if I have a second order, whoops, I left off, that should be a phi, sorry. That's the regular moment cumulant formula. And here's the second order one. You say this fluctuation moment, which in matrices comes from cumulants. So this was actually a cumulant, but now I write it as a sum of some other cumulants. Okay, you could say, what would be the point of that? Well, here's one thing. I hope I'm not stealing any of Daniel's thunder, but if you take the GUE, okay, you can do this in any order. You can look at cumulants of all orders. You take the GUE. Why is that the simplest distribution? It's because all cumulants are zero except the first order kappa 2. But all second order, third order, fourth order, fifth order, all of them are zero. It's the only distribution that has that property. Everything is zero except the variance. So in this subject, that is kind of like the simplest object you could have as a semicircle. Now, of course, to define a semicircular higher order, you have to take those limits of a GUE. There's other distributions that converge to a semicircle, and you might get different fluctuation moments. That would be a different object. So you don't just start with one distribution. So maybe in topological recursion, you start with a probability measure, you get the Cauchy transform that gives you some spectral curve, and then you turn the machine on. Here, we're starting with a whole ensemble of random matrices that gives us moments of all orders. Fluctuation moments of all orders, and then we get we get these cumulants of all orders. So the setup is a little bit different. Well, if you just want to look at the limiting eigenvalue distribution, yes. But what if you want to look at the fluctuation moments, or the third order, or the fourth order, or the fifth order? The beauty of these cumulants is that they're all zero. And why are they all zero? Because this is the part that's kind of a folk theorem. The folk theorem is that for the GUE, and this is more or less worked out in this Hauer-Zagier paper, is that all the moments are given by non-crossing annular pairings. So that, or higher order things, where the cycles all have two elements. And then you see, if you go back to, yeah, what happens if I take something in SN here, there's no, this is just a first order guy, so I just take the regular kappa pi that will kill everything except a block of size 2. So it will only count pairings, and they have to connect the circles. And that's the thing that I think is kind of the folk theorem from Hauer and Zagier, though I'm not certain I've ever seen anybody write it all out. But the in Daniel's Munoz's PhD thesis, when he's going to tell us about it on Friday, he's going to do a more general case, but the special case would be a Gaussian matrix where everything is zero.
Now, see that Hauer Zagier back
Yeah, I never really I kind of for third and fourth you can diagonalize the fluctuations with Chebyshev polynomials. I don't know if that's what you're thinking of. Right, that's before they go to before they go to the limit. Yeah. So yeah, so here's the thing about Daniel's thesis is that normally you take a Wigner matrix. That means you don't assume anything about the distribution of the entries except that it's centered and has variance 1 and maybe some growth of something, but moments don't do crazy things. And that's it. You just get a semicircle law. But suppose you want to recover the distribution of the entry. These things can reveal it. When you go up, in these order, you go down in the distribution of the entries. So so the entry is a random variable. It's got some classical cumulants. And so you can recover. So, I mean, in the case of Daniel's thesis, it only goes up to the 6th cumulant of an entry because we will go up to 3rd order. And yeah, hoping to go all the way, but it's complicated. Mostly, I mean, in the physics literature, you often see, universality. We don't care about those distributions. Well, the point is, can you recover? Yes, you go to these higher order cumulants. These higher order cumulants actually detect this. So it's kind of like a transform. You take some classical cumulants of an entry and you turn it into some free cumulants of some limiting object.
Case of something like easing,
yeah,
studying distribution of the spin.
Yeah.
At each side, it's a kind of order parameter.
Yeah.
Space transition.
Right. There's another thing, where you take a cyclic product of entries of your matrix, and then you scale it right and take a limit, and you can get a higher order free cumulant. So that's in this paper from 2007 up to levels 1 and 2, but Daniel went up to level 3. 3rd order, yeah, which is I think completely unexplored territory until very recently. Well, you just take 3 circles. Once you see how to go to 2, it's pretty easy to see how to go to 3. But anyway, maybe it's not that easy. Anyway, Daniel, I hope, explain on Friday. Okay, so here I just wrote down. How to write, so I'm calling alphas these moments. So I did this because when I did this typesetting, I used alpha. I wasn't going to try and do anything weird with find and replace late at night. But so what it shows you is, for example, alpha 1, 1, that's the 1, 1 second order moment, is a second order cumulant, kappa 1, 1, plus a kappa 2, which is a first order cumulant. And
Why doesn't that kappa 1 squared?
Kappa 1 squared would correspond to a block of size 1 on each cycle, but no connections. And we're only doing the connected things. So that's the equivalent of so you must join them together, and that gives you a kappa 1, 1. And yeah, so here kappa 1, 2, this means one block of size 1 on one circle, one of size 2 on the other circle, and they're joined by the U. So the U is the thing that puts the comma in, right? I guess, you could even define some kind of, maybe like make a machine where you would take a string of classical cumulants of the blocks of pi, and you do one of these like free differential things. And every time you found a comma, you'd found 2 things, you'd glue them together and put a down in the subscript. No, maybe I'm getting a little too crazy. But you could probably make a machine that would crank these formulas out like that. Okay. So because you pair them up in all possible ways. That's the thing. You have to consider all ways that you take a cycle in one circle and a cycle on the other circle and take their union to make the second order cumulant. And then when you do third order, it's the same thing. You've got to connect the circles, and you could either take one cycle from each thing and glue it together to make a third order cumulant, or you could glue 2 here and 2 over there. So it's actually, when you go to third order, the complexity really takes off. Okay, and so there's a formula. Now, how did you, I'll say in a second how you could write these things down. You can also go backwards in the sense that I can write a cumulant as a sum of moments. Okay, so if you want to solve for the cumulants, okay, you can do that in terms of moments. Okay, maybe those formulas aren't so exciting because I have pluses and minuses, and it's even more complicated. These coefficients here actually count certain things of kinds of diagrams, actually, but I'll leave that. And now let's just go to the generating function. So in my last lecture, I'm going to try and explain a little more how you get this. But let's just remind ourselves. So go back to Wojciechowski. We had R and G. R is the R transform. G is the Cauchy transform. And they satisfied this relation. And I showed you how to do that by parameterizing the block that contains one particular point, which we chose to be 1. We'll use the same method to get a formula here. So we make a second order Cauchy transform by taking these fluctuation moments. Now it's going to have 2 variables. And we make a second order R transform. Notice that we don't have that degree shifting going on. R and G are each shifted, right? I mean, in G, the exponent of n of z is 1 more than the subscript of alpha, and it's the other way around for the R. So one shifted one way and the other shifted the other way. Using the C and the M, we got rid of the shifting, right? That's another way of doing the same thing without doing all the shifting. Anyway, here it seemed better to do it this way. So no. So this one is shifted and this one is not. Well, okay, the thing is, it took 6 months to find that formula. If you go and do that, it might take another 6 months. So, yeah, anybody who wants to, the code is there if anybody wants to play with it. So the formula is that this second order Cauchy transform is got from the second order R transform by putting a G in the 2 slots and putting these derivatives outside. And then adding this second order mixed partial of the log of a difference quotient. And this thing, of course, can be written without a logarithm. And it's just this. You take the product of the derivatives divided by the square of the difference, and then you subtract. I forget what you call it, Alex. You called this the 1 over z. Let's see, in your talk, you gave it a name. The Bergman kernel.
Yeah, Bergman kernel.
Yeah, okay.
Yeah, actually, Bergman kernel exactly the relation to this.
Okay. Okay, sorry, then I won't call it that. Okay. And so in turn,
Yeah, W002, I showed is not included term, which is kind of normalization term if you want.
Oh, you mean the extra term?
Yeah, the extra,
Oh, yeah,
term,
yeah,
the extra
that's
last
right,
2 terms inside this logarithm.
The extra term
was not in my formulas there.
in the other side of your form.
Yeah, and it's yeah.
It was example as well.
Yes, but you have to go back to the X and else. Okay, I can explain it later.
okay, so my last talk, I'm just going to try and explain as best I can how you get that formula. So the method is exactly what we did in my first talk, where you choose a block containing 1, and then you label some gaps, and then you get some generating functions.
This is the variable version of the formula you had.
That's right. This is the 2 variable version of that thing.
Oh, yes.
Notice with this thing though, if you know the first order guy, G, you just plug it in the right hand side. If you know R and you know the first order G, you get the second order G. But this one is different, right? Because you have to solve for G. So this equation is just something, an inverse of an analytic function. And this one doesn't require you to invert anything. And then there could be other, actually, I know there is another version which Gaetan showed me. And I'll put it on my slide tomorrow, which makes the two. Okay, I better stop now because it's 2 minutes over time and have one more talk to go.
Okay.
Going off another.
That would be like R of Z1, Z2.
Right. That's Andrew's multivariable part transform, which is a non-commutative variables, and these are just commuting parameters, which could be complex numbers, and it's a little hard to give some meaning to this as analytic functions, but there are a couple of cases when it's out. But actually, because of the log and the difference quotient, it's actually quite hard to make sense of this analytic. Because you have to find a domain where everything is defined.
Go over Riemann surface.
We have any questions? Yes, please.
Is it possible to write a formula for instead of GM, like the taking the moment generating?
Yeah, so in our paper we did it, converted it into this, because that's what people were. Proof was actually using the cumulative generating function and a moment generating. That's how I'll do it tomorrow, and then convert it to these R and G. Though it's quite easy to go back. I mean, once you go from the thing has actually the other one. Okay, you have to place Z 1 over Z and then multiply everything by another 1 over Z. Shift.
Any other questions from the Zoom audience? Maybe? So then let's thank Jamie again. Take 5 minutes break until we prepare Claudio's talk. Maybe I can